Oh wait, let me check. It's arriving between 9 a.m. and 11 a.m. Should you have your
Okay, welcome back everyone. We're going to start a new unit here. Should be the electric potential. Maybe I didn't publish it yet. I will do double check. Yeah, so this stuff that I'm going to start today is not in the test, right? It's not in the test next week. The test next week only involves Gauss's law and electric fields and charges and forces. Chapters, I believe, 21 and 42. This is 23. It's the electric potential and potential energy. Okay? So in order to start this chapter, we're going to talk about potential energy. You may recall you had the gravitational potential energy and spring potential energy from mechanics. You can associate a potential energy with conservative forces, but not non-conservative forces such as friction. Okay? So there are two types of forces. We have conservative forces, non-conservative forces. How do you know the force is conservative? Let's say here's point A and here's point B. Okay? Here's point A, here's point B. Think about the amount of work a force does. If you take an object, if you apply a force from A to B, you go directly, straight line, versus going through some other path. Is the amount of work done through this path versus this path versus some other path, is the work done in general the same?
Yes.
No. In general, no. But for a specific class of forces, called conservative forces, the amount of work is actually the same. It's path independent. It doesn't matter how you get from A to B. If the force is conservative, it means the work done is going to be the same whether you go through the short path, the long path, or any other path. For example, the force of gravity is conservative. And if I have this piece of chalk, let's just think of piece of chalk is for this. It's at the ground, that's the initial, and then the final is going to be at this table. Initial, final. So let's say I take some other path. I start here and I wander around, that's the final. Is the work done by gravity different? No. It's the same regardless of the path that you take, as long as the initial and final points are the same. That's what gravity is. Conservative force. So the conservative force can be stated in two different ways. The amount of work done is path independent. So conservative force. I would give conservative force is this. The following symbol. FC. FC for conservative. Okay? FC for conservative. So the work done is path independent. Path independent or does not depend on path. Okay. Another way to state it is this. By definition, work is this. It's force times displacement, right? F dot dr or ds. Upward dr. If I go over a closed path, this is a closed path. The work done, if it's conservative force, Fc, Wc, the conservative force Fc, is always equal to 0 if it's a conservative path. The work done is equal to 0. For example, let me show you this. Here's again this bottle, and let's say I'm here. Take the bottle around everywhere, and then come back. What's the change in potential energy? Zero. If you come back to the same point, the change in potential energy is equal to 0. So the work done by gravity is actually equal to 0 as long as I come back to the same point. So over a closed path, come back to the same point. The work done is equal to 0. I think this is something you saw before, right? Next. We're going to recall the definition of potential energy. Potential energy. involved the first 20 or 30 minutes or so would be just a review of what we know from before so that we can apply it to electricity. Potential energy. As you know, potential energy has the symbol U. The change in potential energy, delta U, is defined as follows. You need a conservative force to define a potential energy, and it's equal to this minus the integral from point A to point B of that conservative force dotted with displacement. That's the change in potential. This is the definition of the change in potential. I'm going to apply it to a specific problem that we have done, just to be familiar with it, just to review. A specific problem in the context of gravity. So, an example. Here's the x direction, here's the y direction. Okay? And we're going to, yeah.
Sorry, did the delta U equation have F or FC?
It has to be a conservative force. So, the force has to be conservative. Because otherwise, if you just say from A to B, you have to specify the path, right? If it's a non-conservative force, you have to specify the path. But yeah, yes.
So potential energy only exists for forces that.
Yes. You can't have frictional potential energy, for example. Yeah. So, the example, I'm going to do it specifically for gravity. What is the gravitational potential energy of an object at the height h? mgh. Okay, so I'm going to apply this to remind us of that, right? So we need to get mgh here. Let's say I take an object from here, from y initial, to some y final. The object was here initially, and then we're going to raise the object. And the height, which is y final minus y initial, is h, right? That's the height. Final times h. So I'm going to ask you, in what direction is the displacement here? Upwards, right? So a small displacement in the y direction, dr, is a small displacement in the y direction, so it's just dy j hat, right? In this particular problem. The force will be, if I have a mass m in the gravitational field g, what's the force? Minus mg. Yeah, it's mg, but it's in the downward direction. Correct. So F dot dr, what's the dot product of these?
1.
So it would be what? Negative?
Mg.
J hat dot j hat is 1. So negative mg what? dy, yes. So delta U, the change in potential energy, would be minus integral from y initial to y final of the F dot dr. So you get minus y initial to y final. F dot dr is minus mg dy. Minus minus is plus, so you just get mg. When you integrate, you get mgy from y initial to y final. So this becomes mg times y final minus y initial, which is what? Mg h, as you're familiar. That's just a quick reminder of this. The next thing I'm going to do is work energy theory, just to remind ourselves of that. Work energy theorem. What's the definition of kinetic energy? K is kinetic energy.
Change in speed.
1/2 mv squared. V is the speed, right? It's the
Yeah,
magnitude of velocity. So magnitude of velocity squared. So it is 1/2 mv dot v. Because velocity dotted with itself, a vector dotted with itself is just its magnitude squared. So again, all this will be familiar, but it's worth remembering because we need to remind ourselves. So let's take the derivative with respect to both sides. Time derivative. Derivative with respect to time on both sides. So I have this. I want to take the derivative of this with respect to time. The half is a constant, the mass is a constant, it's the velocity. But I have a product. What's the derivative of a product? By the product rule. Yeah, so it would be this. 1/2 the mass of that dv dt dotted with v plus 1/2 mv dotted with the derivative of the second, right? Okay. What's dv dt?
Acceleration.
Acceleration. Well, here is another acceleration. dv dt is a again. So you have v dot a and a dot v. Is there a difference between a dot v and v dot a? No, the dot product is commutes, right? It doesn't matter the order. A dot b or b dot a is the same. So basically this term and this term are the same. So when I add them, the half goes away, right? So it just becomes m a dot v. Is that clear? So it becomes this. dk dt m a dot v. So this is, what's ma? Yeah, it's the net force. Yeah, the net force on the object. Remember this? It's the power, right? Force times velocity. It's the rate of change of energy. dk. Now, what's velocity? Velocity is the rate of change of position, right? It's F dot R. So now I'm going to think about this dk by itself. By basically multiply both sides by d. So what do I get? dk equals to what?
F dot dr.
Yeah. F dot dr. It's dv. That's okay. Now, I'm going to now integrate both sides. From this one, maybe the kinetic energy at the initial position was some initial kinetic energy, K initial, some K final. Sorry, my K's are not so nice, but that's K. R final. Okay. What does this become when you integrate dk?
Change.
You get K, so K final minus K initial, which is yeah, changing K, delta K, yeah. Delta. Okay. What is this? This is work. That's work. This is the work. We'll worry about the U in a moment, right? Someone said U? Yeah. So we'll worry about it in a second. So this is W. That's the work. So remember work energy theorem says the work done is equal to the change in kinetic energy. Now, when you say F equals to MA, MA equals to, the net force equals to the mass times acceleration. Does Newton's second law require the forces to be conservative, or they can be any forces? They can be any force, right? You can have friction, you can have anything. So this net force here, you can't yet say it's the potential energy. So you can have here conservative forces and non-conservative forces. Okay? So first of all, this is the work energy theory. So now I'm going to get to conservation of energy using this. So we're just running through what we learned from mechanics so that we review and then we get back to electricity. So this statement here is just the work energy. So in general, so now conservation of energy. In general, the force can be the sum, can be broken down into two types of forces: the conservative forces plus the non-conservative forces put together. Conservative forces on one hand, you could break down the forces, right? Maybe you have a spring, and you have gravity acting on the system, and maybe you also have friction. So you have two conservative forces and another non-conservative. So you can always break them down. Some conservative ones and some non-conservative forces. So let's look here for this. I have this. Delta K, changing kinetic energy, is equal to F, but F is Fc plus Fnc. Fc means conservative, Nc means what? Non-conservative. Okay, good. So my abbreviation is clear, right? Okay. So I'm going to, this integral here will become two integrals, because F is Fc plus Fnc, so it'll have the work done by conservative forces plus the work done by the non-conservative forces, right? This work can be work done due to conservative ones and work done due to non-conservative ones. So I have delta K minus Wc, conservative work, is equal to Wnc. What is this? Work. Which work? Conservative or non-conservative? Conservative. So this one here is Wc. I forgot to write that. I should have done. This is minus Wc. So minus Wc is delta U. So minus Wc is delta U. So this is delta K plus delta U. So I get delta K plus delta U is equal to the work done by non-conservative forces. Okay? So suppose, what is energy conserved? Mechanical energy. What is it conserved? So when the work done by non-conservative forces is equal to zero, right? So you've got basically no friction, maybe no air resistance. So meaning the work done by these is zero. Work done by non-conservative forces simply is equal to zero. So if W and C is equal to zero, then I get this. Delta K plus delta U is equal to zero, right? So this is conservation of energy. Let's put it in the familiar way. What is delta K? It's K final minus K initial, right? Delta K is K final minus K initial. And delta U is U final minus U initial equal to zero. Let's collect the terms together. K final plus U final. And move the K initial and U initial to the other side so they become positive. So you get K initial plus U initial, right? So it's saying the kinetic energy plus potential energy at the end is equal to the kinetic energy plus potential energy at the beginning. So it's a constant. So it's conserved. Kinetic plus potential is known as mechanical energy, right? All right, that's what I wanted to say, what I wanted to review, and now I'm going to apply it specifically to our electric forces. So you remember gravitational force was a conservative force, G m1 m2 over r squared, it was a conservative force. The electric force is also a conservative force. It has the same form. Instead of G m1 m2, you have K q1 q2, and then the rest, 1 over r squared and r hat, everything is the same. So it is a conservative force. So we're going to associate a potential energy. So the question is, what is that potential energy associated with electrical forces? Electric potential energy. That's the next, basically, topic. potential energy, specifically between two charges. Electric potential energy between two charges. So the force between two charges, let's say I have here charge 1, Q1, and charge Q2, and the distance is R. What's the force between? Yeah, the force is K1, Q2. The force that 1 applies is 2 divided by R squared, R hat, right? I'll put 1 over 4 pi epsilon naught K. Usually we like to put it that way, but I'll just keep K because it's quicker to write. So let's say Q2. Let's say Q1 is fixed and Q2 is displaced from some initial to some final. The question is, what's the work? And so therefore, what's the change in potential energy? So meaning this. So let's say initially it's at some R initial, and then it will be displaced. This charge, let's say, displaces to here, to some R final. And the question is, how much work is required to do that? What's the work? Well, W, by this conservative force, right, WC, let me write it this way. The change in potential energy, delta U, will be minus F dot dr from R initial to some R final. Where did I get this equation from? From here, right? By definition of potential energy. So, since this is the first time we're doing this one, at least today, I'm going to write it fully. So I get delta U is equal to minus integral R initial, R final. I'll write F first. K, Q1, Q2. Over R squared and then R hat. Dot product with dr. What's dr? Right. dr, it's a small change in this direction. How do I say a small change in that direction? dx, okay, could be in the x direction, or dr,
Dx,
and then r hat. Right? dr, r hat. Small change in the r direction. Yeah, if you're specifically moving in the x direction, then this r hat will become I hat, right? If we're moving in the x direction. Yeah, it is dr, and it's that small displacement is in the r hat direction. R hat dot r hat is 1. 1. It's a unit vector, yes. It's 1. And so you end up with basically K Q1 Q2 over R squared dr. Okay? K Q1 Q2 over R squared dr. So you end up with this. Delta U equal to minus K Q1 Q2 R initial to R final, and then 1 over R squared dr. That's it. What's the antiderivative of 1 over R squared?
Minus 1 over R.
Yeah, minus 1 over R. And there is this minus sign waiting, so it becomes positive. So you get this, K, you get delta U is equal to K, U1, U2 over R evaluated between R initial to R final, right? The minus sign goes away because the integral we get its own minus sign. So here you will get, now let me write down explicitly, delta U is U final minus U initial. So this becomes K, U1, U2 over R final minus K, U1, U2 over coded here. This would be said to be our U final, and this will be U finish. So, in general, U at a particular position R, so U of R is K U1 U2 over R. So if it's R initial, you'll have R initial. R5, R5. So in general, for any R, it's that. And again, K is 1 over 4 pi epsilon naught, so that. So notice the potential energy is similar to the force, isn't it? But instead of R squared, you have R. Because you integrate it. Instead of squared, it becomes R. Second thing to note is that potential energy is obviously a scalar, whereas the force is a vector. Force is a vector, potential energy is a scalar. And then the third thing, potential energy has a force has units of Newton's. Potential energy is in what units? It's energy, so joules. Newton's vector. The final thing I want you to note, what's the potential energy if the two charges are infinitely far apart? They're very far away from each other. Zero. Zero, the point of zero potential energy is when the two charges are infinitely far apart. So if you're asked, you have two charges and they're a distance r apart, what's the potential energy between them? Okay, so 1, 2, 2 over r. The potential energy could be positive, could be negative. And if they're very far away, it would be zero. If the two charges are both positive or both negative, the potential energy would be positive or negative? Be positive. Minus times minus becomes plus. If both are minus, if both are plus, it's plus. But if they're oppositely charged, it would be overall. Okay, let's do an example here. And that example is with some numbers. Okay? So let's say you have charge 1, it is positive. It's in the notes. I'm sorry, I guess I did not publish them. I will do that after class. I have a minus charge. This is Q1 is equal to positive E, and Q2 is equal to minus E. Okay? And this is the distance between them, R initial. So let me write it here. R initial is 10 to the minus 13 meters. And let's say both charges are, they have the mass of an electron. One is plus, one is minus, but both have the same mass as an electron. So I will ask the actual question in a moment, but let's go through the following conceptually to make sure we understand what's going on. If you have a plus and a minus, you place them here and you let go. What happens? They will collide with each other, right? They will run into each other. Right. Let's say I give this one some speed to the left, and this one some speed to the right. So let's say this one is given some speed v to the right, and this one some speed, same speed but to the left. Let's say that speed is not high enough. What happens? They will move away, and then they will stop, make a U-turn, and come back and then collide, right? Yeah. Because they didn't get far enough apart. So the question is this. What's the minimum speed that I can give them so that they never come back? I want to give them enough speed that they will go very far apart. Because if they go just far but not far enough, they will still come back, right? Yeah. So how far do they need to go? Infinitely far away. They need to go infinitely far away till the force begins with zero, right? So what's the minimum speed so they get infinitely far away? So find V so they never come back. Find V speed. So they never come back. And I always ask, you have options to solve this problem. The two options are, you got Newton's laws, and you got, what's the other approach? Conservation of energy. That's the other approach. Which one is better? Conservation of energy is far better. Why is the force approach not a really good approach in here? Think about the forces. Yeah. To apply Newton's laws, right, you have to say F equal to ma. Is F constant? No. The more away they move from each other, the force is kq over r squared. They will. The force is not constant, so the acceleration is not going to be constant, and so you will have a non-constant acceleration problem. So you don't want that. So you want to use conservation of energy in this case. Okay. Is energy conserved in this case? Yeah. Yeah. Is there? There was no word on friction or anything, right? The only force between them is the electrostatic force, the Coulomb force. So yeah. So use conservation of energy. Conservation of energy says this: the kinetic energy at the beginning plus the potential energy at the beginning is equal to the kinetic energy at the end plus the potential energy at the end. That's conservation of energy. Now for kinetic energy, let's think of the right side first. Where do I want them to be at the end? Where do you want them to end up? Infinitely far away. So what's the potential energy at the end? Zero. Zero. They're infinitely far away. How fast are they moving when they move infinitely far away? If you gave them just the minimum speed, they're barely moving. Yeah, so zero. You can give them more speed so that when they're infinitely far apart and they still have more speed to go. So it means you gave them too much. We want the minimum speed. So we want them to get, when they get to infinity, in practice, very far away, they're barely moving. So they just stop. So we want this to be how much? Zero. They're barely moving. They get to that. So both of these are zero. So on the right side, I have zero. So that's the right side. Let's look on the left side. Kinetic energy. Do I have one object moving or both? Both of them. And both of them have the same mass, right? So it's just 1/2 mv squared and another 1/2 mv squared. So I'm going to write it. So the first one has 1/2 mv squared, and the second one also has the same mass and speed, 1/2 mv squared. Plus potential energy at the beginning. All right, that's the new thing, right? What is the potential energy between 2-point charges? K Q1 Q2 over R, right? K Q1 Q2 over R. I'm going to substitute numbers. I'll just use the K because it's 9 times 10 to the 9. So I would just write K and then Q1 and then Q2 over R. Just R. R initial. Add these, you just get mv squared plus K. What's Q1?
1.
One of them is E. How about the other one?
Also,
Yeah. Yeah, minus. Then R initial. 0. When you move it to the other side, it becomes plus. So I get M E squared is equal to K E squared over R initial. Solve for D. So we need to plug in the numbers, right?
which button? Sabi sa masukin. Even though masukin. Tapi in every kind of problem ko. Gaya kasi na
Yeah. Square, yeah. Oh, I did square? Yeah, square. Should be what, 8 point? 8. Should be. Something times 10 to the 7. About 5. Yeah. I'll put 5 times 10 to the 7, approximately. I'm interested in just applying the conservation of energy, not the actual. Yeah. Oh, this one is moving, right? So it has kinetic energy 1/2 mv squared. This one is also moving, so it has 1/2 mv squared.
like can you like explain once again why is the K final is 0?
Why is the kinetic energy final is
Yeah.
0, right? Yeah. So where do we want them to be?
It's
At
like
the end. How far apart?
very
Very far. Okay. If I'm giving them just the minimum speed to get very far, how fast would you want them to be? If you gave just the minimum speed. So let's say plus minus. They move very far apart.
yeah.
I gave them just the minimum speed to get there. How fast do I want them to be? Very fast or very slow?
Very
Initially, it would be very fast.
Yeah.
As they move away, they would be slowing down or speeding up.
oh very sweet.
They'll be slowing
Slow,
down
slow,
and
slow.
slowing down and slowing down. By the time they get to infinity, or very far, how fast are they moving?
Oh 0.
About 0, right?
About
Yeah.
zero, yeah.
So that's it.
Oh.
Yes.
So I know with gravity that no matter how far the distances, there's still gonna be an effect between two objects.
There will be a what?
There'll still be an attraction between two objects.
Yeah.
Is
Unless
that-
they're infinitely far apart.
Yeah, is that the same for?
Yes.
Okay.
Unless they're infinitely far apart. And that's why we say far enough, but that's infinite.
Okay.
Pwede po siya sa K final po sa mga kaya
What?
padahal o dito bigat tapos sa
No, if you do microscale, it is still the mechanical energy. The definition is the sum of the kinetic plus the potential energy. Kinetic energy plus potential energy. On the microscale, because for example,